Carrier waves. Radio transmission allows us to send information over much greater distances than the sound or image could travel on its own. Different wavelengths of radio wave travel in different ways and require different transmitters and receivers. For example, long wavelength radio waves diffract around the Earth's surface. Short wavelength radio waves are refracted by the ionosphere, returning to Earth. Effectively, it's as if they're reflected by the ionosphere. Microwaves pass through the ionosphere. If we produced a radio wave from a sound, it would contain a wide range of wavelengths, each travelling in different ways. They may get broken up on their journey. What we can do is add our required signal to a wave of known wavelength, called a carrier wave. The signal effectively has a piggyback ride on the carrier wave, and the carrier wave can be removed when the signal reaches its destination. The carrier wave will be of a higher frequency than the highest frequency found in the signal. The two main ways this is done is by altering the amplitude of the carrier wave or the frequency of the carrier wave. We'll look first at the method of altering the amplitude. Here we have the high frequency carrier wave and the much lower frequency signal that we want to transmit. What we can do is have a wave like this, where, as you'll see, it has the overall frequency of the carrier wave, but the amplitude is varying in line with the signal. So here the signal has a low amplitude and the combination has the low amplitude. Here the signal has a high amplitude and the combination has a high amplitude. This is called amplitude modulation, or AM. The amplitude gives the amplitude of the signal, and the frequency of the changes gives the frequency of the signal. What the radio does is filters out the carrier wave and leaves behind the signal wave. So the radio will receive this, it knows this and so can remove it, leaving behind this, which is what we wanted to transmit. We'll now look at the second method of encoding the signal onto the carrier wave. Again, we have a high frequency carrier wave and a lower frequency signal. The combination now looks something like this, where the high amplitude of the signal is shown as a higher frequency in the combination. The low amplitude of the signal shown as a lower frequency of the combination. You'll see that the frequency rises and falls as the amplitude of the signal rises and falls. This is called frequency modulation, or FM, and the magnitude of the frequency change gives the amplitude of the signal. The number of times the frequency changes per second gives the frequency of the signal. The radio again filters out the carrier wave, leaving behind the signal wave. So again the radio will receive this, it will take out this, and it then can read the signal. Amplitude modulation, or AM, is the system used on the medium wave and long wave bands. You may have seen MW and LW on the dial of your radio. It is more susceptible to noise, as noise tends to affect the amplitude of a wave. Frequency modulation, or FM, is used on the very high frequency or VHF band of a radio. It's less susceptible to noise, as noise does not affect the frequency of a wave. For both AM and FM, the higher the frequency of the carrier wave, the more information can be carried. The carrier wave must have a much higher frequency than the signal we're carrying. It's the carrier wave that your radio tunes into. Bandwidth and sidebands. When we add the carrier wave and the signal wave, we get frequencies other than those of the carrier wave and the signal. If the signal was a single frequency fs, frequency of signal, and the carrier is frequency fc, frequency of carrier, the new frequencies produced will be fc plus fs and fc minus fs. In reality, however, we don't transmit a signal of a single frequency. That'd be a bit boring. So if we have a range of frequencies, fm, we would have fc, the frequency of the carrier, plus this range of frequencies fm, and the frequency of the carrier minus the range of frequencies fm. This is simpler on a diagram. Here we have a line representing increasing frequency, and our carrier frequency could be here, fc. This is the extra range of frequencies fc plus fm on one side, which gives us a sideband. On the other side we'd have fc minus fm, another sideband. So our whole range of frequencies would go from this lowest frequency here to this highest frequency here. That range of frequencies is known as the bandwidth. It's important that a radio station transmitting on this carrier frequency here doesn't interfere with another radio station. So the other radio station would have its carrier wave some way down here, ensuring its sideband does not interfere with this sideband.